Hello guys. You're welcome to this lecture. We are going to start looking at subspaces. In the last lecture or last video, we looked at vector spaces. We gave a definition of a vector space, and we did a couple of examples. I will take you back just to remind you of the definition of a vector space. So we said that given a set V with some elements which we call vectors, again, remember that the name or the word vectors here is used in general, not necessarily for the physical quantity of vector that we know. There could be vectors, or could be matrices, could be polynomials, but all the elements in a vector space are called vectors. Okay, so a vector over a field here of some scalars is said to be a vector space if these axioms are satisfied. So the first one is that we require that V under addition has to be an abelian group, okay, and then scalar multiplication has to be closed under V, and these other axioms must hold, okay. So keep this in mind. This will become important as we look at subspaces, okay. So these are the axioms, if you like, for a given set over a field to be called a vector space. So we'll go quickly back to what we want to look at today. So for this couple of videos, I'm going to look at subspaces. Then later on, we'll look at linear combinations, linear dependence and independence, and then the rest later. Okay, good. So what is a vector space? This video will cover basically the definition of a vector space and a very important theorem that helps you to prove that a given set or subset is a subspace. So a subset W of a vector space V is called a subspace of V if W itself, okay, the subset is a vector space with the same scalars, vector addition and scalar multiplication as V, as the main set. Okay, this is very similar to what we did under groups and rings and fields, where we had, a subgroup, we had subrings, we had subfields, which are basically subsets, and the elements of the subset must obey the same axioms as the main set. So it's very similar to that. Okay, good. So V being a subspace, for W to be a subspace, basically means that it has to be a vector space. And must, if you like, satisfy all the axioms for a vector space that we know. Okay, so keep that in mind. Theorem 7 here is a very important theorem. So basically this video is going to prove this, and then later we'll look at some examples. Okay. So in other words, as we've seen previously, given a subset, in order to prove that the subset is a subspace, you don't need to go back to the axioms of a vector space and check all of them, right? As we did when we were trying to prove that something is a subspace, a vector space. So here, after we've proved this, then we can basically use this conditions here to show that something is a subspace. So the theorem says let V be a vector space and let W be a non-empty subset of V. Then W is a subspace of V if and only if the following conditions hold, right? If U and V are in W, in the subset, then U plus V is in W. And if U is in W and lambda is in F, the field, then lambda U is also an element of W. So given a subset, basically, this is saying that in order to prove that a given subset of a vector space is a subspace, you need vector addition to be closed, right? If I take any two elements in the subset, their sum must be in the subset, and a scalar multiplication must be closed under W as well. So I take a scalar multiplied by any element in W, the result must be in W. Okay, once I'm able to show these two conditions, I can conclude that the subset is a subspace. That is basically it. Now, in some books, in some theorems, in some other material, you will find that they will add, let me use my this thing to write this. They will add a third one. Actually, a first one will be that you want the zero vector, right? The zero vector, whichever way you want to write it, must also be in W, okay? But actually this is implicit, this is implied here, okay? It's implied in the second condition here. So we often don't, that is why we are not separating it out, because if I choose lambda to be equal to 0, right? If lambda is 0, lambda is a scalar. If it's 0, then I have 0 times u. 0 times u is 0, and that has to be in W. Okay, so it is part of this condition, is part of B. So we don't, we're not going to write it out separately here. But it's also important because to check that something is a subspace, one of the easiest conditions you want to check is to see whether the zero vector is actually an element of W. If it's not, then you can easily conclude that it's not a subspace. Okay, good. So that is one of the checks that you be doing. Okay, good. So now that we understand this this theorem, we're going to prove it. Okay, we're going to prove it. So it's actually not a difficult proof. It's an if and only if theorem. So the first one is that we want to assume that W is a subspace. And if it's a subspace, then we prove that these two conditions are satisfied. And then we do the converse, where we assume that A and B are true, and then we prove that W is a subspace. Well, in the converse is where we do a little work, right? The converse, to prove that W is actually a subspace, we have to prove that it is a vector space. And so that means that we must show that, right? If you remember, we must show that W here to be a subspace or a vector space. We must show that it is an abelian group. For it to be an abelian group, there has to be associativity with respect to addition. There has to be what? We need an identity element. In this case, 0 must also be in W. If I take any element U in W, there has to be an inverse, an additive inverse. Negative U must also be an element of W. All right, for it to be abelian, U plus V must be equal to V plus U, right? So this 4, if we show this 4, then we have shown that the subset would have shown that the subset is abelian, right? And then we need to show the other conditions, axioms 3 to 6. Okay, but 3 to 6 will be quite straightforward as well, because W is a subset of V, and all the elements of V satisfies associativity, commutativity, the left distributive laws for addition and multiplication. Because the elements in V satisfy those ones, the elements in W must satisfy them as well. So we can conclude from there. So the most of the work will be here, right? Basically showing that here that there's an identity element, which is 0 is in W, and that every element has an inverse, an additive inverse. Okay, so that is how the proof goes. So it's it's going to be straightforward. Okay, so the first part of the proof, we are going to assume that W is a subspace, and then show that these conditions hold. And that part is straightforward, because if W is a subspace of V, then W is a vector space. But if it is a vector space, then vector addition and scalar multiplication, right, are satisfied. They hold in every vector space. Therefore, A and B hold. Okay, so basically that's the proof for the first part. Let V be a vector space and W an empty subset. We suppose that W is a subspace of V, then it is a vector space, and therefore W satisfies all the axioms of a vector space, and those axioms includes the conditions A and B. Okay, so that is the first part of the proof. The second part of the proof is a sketch, some of the sketch I've done here, right? The second part is now we are going to suppose that A and B are true, they hold, and then we prove that W is a subspace. And to prove that it is a subspace, basically, we need to show that it is a vector space. And to show that it is a vector space, we have to show that it is an abelian group. These guys hold and other axioms hold. Okay, so let's concentrate on this for now. So conversely, suppose that W satisfies the two conditions, right? A and B. Now condition A implies that W is closed under addition, of course, under vector addition, right? And okay, now because all the elements in W are also elements in V, and the elements in V obey associativity and commutativity, the elements in W are also associative and commutative, right? So associativity and commutativity hold in W since they hold in V, and W is a subset of V. Okay. So I guess I hope that that is clear enough. Okay. So this and that, associativity, check. Commutativity, check. Okay, so the other ones we need to check are this and this, that the zero element, the identity element is in W, and that there's an inverse. Once that is true, then we can conclude that we have an abelian group in W. Okay, good. Now, condition B is true means that lambda U is an element of W. Well, to get identity, I can pick lambda to be 0, right? So I take lambda to be 0. If lambda is 0, I get 0 times U. 0 times U, we have proved this already, that 0 times U is 0, the 0 vector. Therefore, the 0 vector is an element of W. So we have an identity element, the 0. So the 0 is in W. So this is checked as well. Now, thirdly, we can also choose lambda to be -1. If lambda is -1, I'm going to have -1 times U, and that gives me minus U. So minus U, if U is in W, minus U is also in W. So the additive inverse is also in W. So this is also checked. So all these four that we need for an abelian group are satisfied. Therefore, we can say that V is an abelian group. Therefore, actually, this is W, right? W with plus is also an abelian group. Okay, good. But abelian group is just one of the axioms, right? Is the most important one, but it is one of the axioms. If you go back to 11 here, or we have the, so we have shown this guy. We have shown that W is an abelian group. This is true from condition B. So this is true. These other ones will be given to us for free because these conditions here hold in V. And all the elements, as I said before, are elements of W are also elements of V. And since the elements of V satisfies this, the elements of W also satisfy these ones. Okay, so we can conclude that these are satisfied, this is satisfied, that is satisfied. Therefore, W is a vector space and therefore a subspace of V. Okay, so that is how the proof goes. So if we can go back and say that condition B implies that W is closed under scalar multiplication, and then the other axiom, that's what I just showed you. The other axioms 3, 4, 5, and 6, they hold in W since they are true for all the vectors in V, and thus are true in particular for those in W. Therefore, W here is a subspace of V. Okay. I hope that is clear enough. It's spend a bit of time on it because this is the most important and critical theorem to prove that a given set or subset is a vector space. So you need to understand it quite well. Okay, good. So here's a remark here. Condition A and B, actually you can show from condition A and B, you can derive this, right? From condition A, we know that, so let me write this out. If I take any two elements in W, the sum is also in W. Well, if I multiply a scalar by any vector in W, the scalar multiplication of that, right, is also in W. Okay, well, so that means that this guy is an element in W. U is also an element in W. So if I add any two elements in W, this guy and that guy, or V, right? it could be U or V, that must also be in what? In W. So you can combine these two to get this. Okay. Also, as I mentioned before, the zero vector must always be an element of the subspace, right? Because if lambda is 0, I get 0 here, and 0 must be in W. So that is the second, my second remark here. So keep this in mind. This is important because this is one of the things you can easily use to see whether, to check whether something is not a subspace. You can straight away check if the zero vector is not an element of the subset. Immediately you can conclude that it is not a subspace. Okay, good. So I'm going to let's look at these simple examples, and then I'll end the video and I'll come back with some more examples on these things. Now, so here, every vector space has at least two subspaces. Okay, so these are trivial examples. Itself, right? If V is a vector space, V is also a subspace. Okay, and the vector with the zero elements is a subspace. It's called a zero subspace. Okay, so V itself and this guy will be subspaces. So every vector space will always have a subspace, like we did for groups, right? You have groups and rings. We have the zero ring, right? And you have the ring itself is a subring, right? The ring itself is a subring, even though it is not a proper, it's an improper subring, but it is a subring in any case. Okay, so it's the same here. So the zero subspace is there, and then itself is also a vector space, a subspace. Okay, let's look at one that is not so trivial, that needs a bit of calculation, right? So example 2 here, let W be a subset of R3 such that W is given by this: A, B, and 0, where A and B are real, with the usual operations of vector addition and scalar multiplication. You want to find out whether you want to show that W is a subspace of R3. Okay, you want to show that it is a subspace of R3. How do we show that? Well, why is it a subspace? Well, if 0 here was not 0 or some C, right, for instance, then W will be R3, right? But because this is 0, this is a subset. So these are elements in R3, if you like, X, Y, and Z. But it's a subspace because here this is always 0. Okay, whereas in R3 this could be 0 or any other number. So it's a subset. Okay, so the form of the elements in the subset is very important. You need that to be able to prove that a given element is an element of a subset. So you have to pay attention to the form. Okay, so all the elements in W must be in this form. You have a real number, another real number, and the last element must always be 0. Okay, that is what shows that an element is an element of W. Okay, of course, the A and B could be zeros, right? There could be zeros or non-zeros, but here the third one must always be a 0. Okay, so keep that in mind when you are trying to find out if something is a subspace or not. Okay, so here the easiest one to check, well, we can easily check that the 0 vector is an element of W, right? 0, 0, 0. You can take A to be 0, B to be 0, so you have 0. So 0, the 0 vector is an element of W. So that is fine. You don't need to worry. So to show that it is a subspace, you go back and show these two conditions. Show that if I take any two elements and add them, the result will be W. If I take a scalar multiply by some element in W, I get the result will also be in W. So basically these two conditions will tell us that something is a subspace. Okay, so that's what we're going to do here. So let's choose W1 and W2 be an element of W, be elements of W. If they are elements of W, then we can write W1 to be of this form, right? W1 can be A1, B1, and 0. W2 can be A2, B2, and 0. Okay, so those are elements in this. Again, every element in W must have a 0 as the third element here. All right. where these guys are real numbers, of course. Okay, good. Now let's add them, the usual vector addition, right? So W1 plus W2 will be this plus that. I add A1 to A2, B1 to B2, and 0 plus 0 is 0. Of course, then I can easily conclude here that this is an element of W because I have a real number, and the third element is 0. So this whole thing here belongs to the subset W. Okay, so W1 plus W2 is an element of W. Then the second condition to test is to multiply a scalar by any of the vectors in W. So multiply by W1. You could have used W2, right? It doesn't make a difference. So multiply that lambda by this. Well, multiply each element by lambda. You get that lambda times 0 is 0. So you have this. Well, this also belongs to W because lambda A1 is a real number, lambda B1 is another real number, and the last element here again is 0. Therefore, lambda W1 belongs to the subset. So those two conditions are satisfied. This holds and that holds. Therefore, W is a subspace of R3. Okay, good. So that is why that theorem is very important. So you use it to do this, to show these guys. So in the next video, I will do a couple of more examples similar to this and some that are different from this one. Okay, and then later on we'll move on to look at linear combinations and linear dependence and independence. All right, so I'm going to end this one here.